All right, let's do some homework. Starting on 610 over here, find each antiderivative. And we are here in the chapter on U substitution. All right, so the first one here, 10x sine 5x squared dx. That's a pretty simple choice. U is going to be 5x squared. Du is going to be 10x dx, like so. So dx can be that, or we can go this route in this case and just substitute 10x for du dx. So we'll rewrite it as integral of 10x. We said we would do du dx here, 10x, that covers that, and then here u dx, and the dx cancels, so we are left with sine u du, and the antiderivative of that is negative cosine, right? Negative cosine u plus c. And then we substitute it back, plug this thing back in for u. So we have 5x squared plus c right there. Okay, the second one, we have b, that is 1/2 square root of x times e to the square root of x dx. It's also a pretty clear choice. The inside function here is the exponent to function on top of e. So we're going to just use that for u. U is square root of x. Du dx equals 1/2 over square root of x. So that's exactly what we need there. So same model that we had before. This here is going to be the integral of du dx times e to the u dx. Dx cancels. We are left with the integral of e to the u du, and that is e to the u. That is e to the u. E to the u. Okay, now we'll substitute that back in. So that is e to the square root of x, right? We're going to put this back for u here. And this is where we attach our c, and that's that. Next one. So this is really just kind of going through the motions in a sense, right? If you look at it this way. So here we have, this is a little, see that is even worth substituting, right? We could just do this direct and go, that is 1/4 of 1 over x dx, and then we can just go direct on this one, right? Couldn't we just do that? ln absolute x plus c. Yeah, I don't see a reason to use substitution for this one, right? We can just factor out the constant, and then we have 1 over x, and the antiderivative of that is natural log of x absolute, and then don't forget the plus c. Okay, now 2, same thing, 2 antiderivatives. This one here is secant squared of 3x squared dx. Okay, well, so the x here is a piece of this derivative, right? It's not exactly the same because there's going to be 6x. So we're going to be a factor of 6 different, but in any case, the derivative of x squared is here, and that's all we need. So we'll just put u equal to 3x squared, and that makes du dx equal to 6x. And that makes x, if we want to stick with our formula here, x will be 1/6 du dx. Like so. Now we're ready to substitute. This is going to be, I'm just going to pull the 1/6 right out of the integral. And then in the integral, I have du dx times secant squared of u. And then here's dx. The dx cancels out. I'm left with 1/6 of secant square of u du. And I can find the antiderivative of that. The derivative of tan is secant squared. So this is just going to be 1/6 tan u. And then I reinsert the u. So we have 1/6 of tan 3x squared. And then here I'm going to put the c. Okay, 1/6 tan 3x squared plus c. Next one, hold on, I need to move something out of the way here. There. All right, this is number 3. Okay, now number 3, let me actually scroll this up a bit. Number 3 is let's go to a new page, is a definite integral. So we're gonna have boundaries here, 0 and 4, from 0 to 4. And then inside the integral, we have x times e to the x squared plus 5. That sounds very familiar to something we've done already. It's very familiar to the one we've done in class in the CYU, I think. So u is going to be x squared plus 5. Du dx is going to be 2x. So we substitute this x here, so we just need 1/2 of du dx. That is going to be x. Now we're ready to substitute. Let's keep, actually we're going to leave the boundaries open for now, because we're going to have 1/2 in the front. I'm just going to pull it out. And then here for x, we have du dx, and the dx is going to cancel with this dx. So I'm just left with e to the u du. Again, same thing, right? So now let's work on putting the boundaries and use the adjusted boundaries for this. The adjusted boundaries will be plugging 0 in for x here. That gives us 0 plus 5. So the lower boundary is 5. And then we plug in 4 for x. That's 16 plus 5 is 21. So from 5 to 21 in the u world. We sometimes call this being in the u world. This is the x world. This is the u world. And the boundaries are translated by simply plugging the x boundaries in for x, where you set u equal to whatever the expression is, and then the result of that gives you the boundary for u. So then the antiderivative of this will be e to the u. So I'm going to plug in the upper value first, e to the 21, minus the lower value, e to the 5th. And no, don't forget the 1/2 in front. Whoops, that's not nice. Don't forget the 1/2 in front and parentheses, and you're done. Okay, for another definite integral is from 1 to 3. And we have 3x plus 1 to the 3rd power dx. This is a 1 here. Let's put u equal to 3x plus 1. That makes du 3x. 3, yeah. No. It makes du dx, hold on. So there we go, 3, right? 3 is what we're looking for. So du dx is 3. And what do we want with this even? Why is this even in need? Oh yeah, no, it is in need of doing this here. This is the outside. All right. So let's see. We have 3du. Let's use the other method here because we don't have anything obvious to plug in. So let's do I have a feeling that this is not going to be easy because 3, no, it is, because we just need the factor. Okay, so that's fine. So let's just go to dx equals du over 3, and that way it's going to become clear once we insert stuff. Let's do that right now. We're ready for it. Leave the boundaries blank for now, and we're just going to put u to the 3 du over 3. That is replacing the x, and we've inserted this here into u. So we have u to the 3rd power du over 3. So that means this 1/3 here is going to go in front of the integral, right? So it's going to be 1/3 of that integral of u cubed du. Now let's work on the boundaries. Let's work out the boundaries. The lower boundary, we plug in 1 for x. That's 3 plus 1 is 4. And the upper boundary is 3 times 3 is 9 plus 1 is 10. And then we're going to carry this forward here. 4 to 10. All right. So now we are finding the antiderivative. And that is u to the 4 over 4. But we have this 1/3 here still in front. So that is it. And well, so we have boundaries. So we'll plug this in here. Let me get the eraser going here real quick. Here's the eraser. Whoa. Okay. Yeah, that should work. So we're going to have 10 over 4 minus, and we're going to just put, hold on. There. We're just going to put parentheses here. 10 over 4, 10 to the 4 over 4 minus 4 to the 4 over 4. Like so. So we can put this as a real number. So this is 1,000 divided by 4. That's 250 minus 4 times 4. There's 1 4 that we can cancel out. So it's 4 to the 3rd. That is 64, right? Minus 64. That's, well, you can do the rest, okay? Wait, there's something wrong with about this one here. This is actually 2,500. There you go. So that here is 812. There. Okay, that's 4. See if we can get all the way through here. What is this one? Selected values of a differentiable function. Well, and this isn't quite in the picture here. There, now we see everything. Set how a different function f is a derivative f prime are given in the table. Evaluate. So we have the prime on the inside. That's good. But now we have an inside function here. So let's see how this works out. Let's go 5. And we have the integral from 1 to 4 of f prime of 2x. So we have an inside function and an outside function. So we're going to do u substitution. U is equal to 2x. du dx, du is 2 times dx, 2 dx, right? So dx is du over 2. And now we can put this in. That means we're going to look for the integral. Let's just put the boundaries here right away. So 2 times 1 is 2. 2 times 4 is 8. And then on the inside, we have f prime of u And then here for the du, we have to be careful. We have du over 2. So let me again put the 1/2 out front and just leave du left over here. And we're ready to insert. Now, f prime, we only need to know that we're looking here now for f of 8. So this is f of 8 minus f of 2, and we're done. And so for this, we look this up in the table. F of 8 is 4. Oh, but be careful. Do not forget this factor here. 1/2 of this. So f of 8 is 4 and f of 2 is 7. So 4 minus 7 and the whole thing times 1/2. And then we have 4 minus 7. Sorry, this handwriting is not so good today. So it's -3. So it's -3 over 2, right? Yes, correct. Okay, very good. Now let's scroll onwards. Let's see if we can get the whole thing done in the time that I have. The graph of y equals f of x is shown for -1 to 2.5, where f of x equals this thing. Let R be the signed area. Signed, so that means this here is negative, this here is positive, this here is negative, this here is positive. Between the curve g of x equals cosine x and the x-axis. Between x equals 1 and x equals k for some constant k. Find the value of k so that t equals r. Okay, well, this is a little tricky. Because, so we have this picture, and now we need the cosine function, g of x. G of x is not here. This is only f of x. We need g of x. So g of x goes like this. It comes over here, goes down. Let's see, this all goes to 2.5. All right, so it goes from 1, it crosses at pi over 2. Pi over 2 is about little less than 1.6, so that's about right here. So we're coming from here to here, and then we're going down to -1 by the time we get to pi. So that's outside of the range. Okay, so I don't know how to apply my letter here, my crayon. So, need to maybe figure out how to do this. So, but the point is, cosine of x starts somewhere here and then goes down and then goes over there. So it's just a visual, right? We don't need to do it visually. Let's just see what's going on. What we need is an integral, right? So this here is f of x. So we first find the integral. Let's see if I can make this nicer. Whoa. Whoa. What happened? Okay, so we're finding the integral. Let's start with the integral. Integral that R be the signed net area between the curve and the x-axis as shown. So we're going to go from -1 to 2.5. And that's going to be the area of 2x cosine squared of x. No. That's not it. That is different. That's a different thing. Cosine of x squared dx. Okay. So that is the net area of this. And now we're supposed to find the difference between t. So this is r. R is this thing. Let's just, I wonder if we even need to find r. I wonder if we even need to find out it. R is the signed area between the curve and the x-axis as shown. Okay, fine. Now t is the signed net area between the curve and the x-axis between x equals 1 and x equals k. So this is a second thing here. So t is equal to the area between 1 and k. We don't know what that constant is, of cosine x dx. Okay, so that's t. All right. Find the value of k so that t equals r. T equals r. Okay, well, so we need to find this one first, and then we find this one, and then we see how we can compare them. Let's start with this one. This is an easier one, right? So the antiderivative of cosine is minus sine of x. So this is going to be minus sine of k minus sine of 1 there. Yes. And that is, let's clean this up just a little bit. We need to have, let's see how we do this. It's basically sine 1 minus sine k, right? Just eliminate as many negative signs here as possible. I think I did this right. So this is plus sine 1 and then minus sine k. Yes, that'll work. Okay, so that's this. That's t. And then let's find r. So for r, we need u substitution. So u equals x squared. Du dx equals 2x, and that's ready to insert. So let's insert it. So we're going to have the area here from, let's do the boundaries. -1 squared is 1. And 2.5 squared is that 6.25 maybe? I'm going to grab my calculator here real quick for this so that we don't make silly mistakes. So we have 2.5 squared, yeah, equals, yes, 6.25. Okay, so that's 6.25. And now what goes on the inside? Everything gets substituted. The dx cancels out, and we are left with cosine of u du, right? The u dx is substituted for x, 2x is correct. Then that dx cancels, so that leaves us just with du. And then cosine of u is here in the front. And that makes this problem much easier than we thought, because now we have exactly the same expression here. We have cosine u du, cosine x dx. We have the same lower boundary, so that can only be equal if k is also equal to the upper boundary here. So this is, without further ado, k must be 6.25. And that's the end of this one. Kind of like way more complicated in the setup than it comes out in the end. But see, it's a good thing to just do this boundary recalculation here, boundary reset right away. As soon as you go into the U world, you need to put the boundaries into the U world as well. And then that makes it actually pretty simple. All right, we're going to number 7. Using the substitution of u that give us the substitution. Okay, fine. So then let's write the integral, -1 to 2 of 4x times the square root of x squared plus 6 dx is equal to which of the following? Okay, well, that should be pretty simple. We are going to make u equal to x squared plus 6. That makes du dx equal to 2x. Now we have 4x here. So we could just go, well, what is 4x? 4x is 2 du dx, right? And that will take care of that. Then this inside here is u. This here is replaced by 2 du dx. The dx cancels out. So let's do that. And we'll leave a little space in front of the integral, and we'll leave the boundaries blank. And let's just write the substitution. So we have square root of u du times 2, right? The 2 goes into in the front now. I'll pull the 2 into the front, although it may not be this, right? But we'll see. So then we have the boundaries, -1, x squared is 1 plus 6, that's 7. And then 2 squared is 4 plus 6 is 10. So 2 times from 7 to 10 square root u du, and this is d, right? Beautiful. Let's go on. Number 8. Ooh, we're going to get this completely done in the time I have. All right, number 8 is, it is known for a function g that this thing equals 12. Which of the following statements is guaranteed to be true? Let's see if we can just have something fall off the truck. So we have 3x on the inside. This is basically a substitution here. So we just have to substitute. Let's just say t in this case equals 3x. Let's see if we can make this quick. And that gives us, well, no, we need to find dt dx. Okay, let's find dt dx. That's going to be 3. So replacing dx will give us, dx will be dt over 3. Okay, now if we replace it, we'll get the integral of g of u sorry, t. I should have done t here. We're trying to confuse us with t substitution instead of u substitution. So g of t, and now where are we? Dx, this is dx. So times dt over 3, I'll pull this into the front, and now I'm going to do my interval, my boundaries. So we're looking for 3 and 9, and that have to be fitting in here. So 3 times 3 is 9, that's my lower boundary, and 9 times 3 is 27, that goes on top. All right, does this look like anything? Oh, well, let's see. Do we have multiple that can fit with the boundaries? Yes, we do. So the first 2 fit. Do we need to actually solve it now so we can have the number? I guess so, eh? That's weird. That's weird. That's weird. It kind of feels like it should be scaling up. So that's the question, right? It's the boundaries have a scale factor of 3 times 3. Seems as if that should be 36. I would bet on 36, but let's see if we can figure this out precisely. So if g of 3 of x, g of 3x, 3 times, okay, let's do it this way. If g of 3 times something, and that something, the upper boundary is 9, so 3 times 9, g of 3 times 9, 3 times 9 minus g of 3 times 3 equals 12, then the question is g of 20, wait, 9. Hold on. I'm getting confused here. I'm getting my wires crossed. G of 3 times 3. No, that's a boundary. That's lower. Okay, I'm still good. 3 times 9 minus g of 3 times 3 is equal to 12. Now I have g of 27 minus g of 9. Okay. Ah, look at that. Okay, right. The key is here, right? So 1/3 of this. These are the same, right? This is all the same. So the inside is the same. So 1/3 times 12, that is 4. 1/3 times 12 is 4. 3 times 3 is the minus. That's this one here. So it's correct. And this is 9 that goes in here. But this scale factor 3, where did this come from? We have dt dx equals 3. That's correct. So that makes dx, which is what we're replacing, equal to dt over 3. That's correct. So once we replace the dx, it becomes dt over 3. That means 1/3 can be factored out to the front. So now I have the adjusted boundaries. Let's see if we adjusted the boundaries correctly. T equals 3 times x. X, the boundaries of x are 3. That's 3 times 3 is 9. Upper boundary is 9. 3 times 9 is 27. That checks out. So this integral expression here is correct. Now, if we plug this in, we get the same thing. We get the same thing. The weird thing is that they don't have the 1/3 in front of this, right? So if 1/3 is supposed to be the same, so this here, 1/3, here you go. Yeah. So 1/3, let's get rid of all this stuff here. I think I got it, but I want to make this a little clearer and cleaner. So we've done the U substitution. So we know this thing here. We know this thing here is the same as the original interval. So this here is 12. And we don't have to do all this stuff that I did before. We can just go here and say, okay, this, we know that this is the same. This is the same as the original, including the different boundaries and including the 1/3. So this is the same as the original over here. But now if I evaluate the integral without the 1/3 in front, I'm going to get this. It's really going on my... This here, gt dt, is now dt, that's a t, that is now 3 times 12, right? We multiplied this side here by 3, now we're multiplying this side by 3, and that is 36, and so it's A. There you go. That's how it works. A is the right answer. Okay, now we got a little bit behind on this one. Let's see if I can do the other. Oh, it's the end. It's the end. There's only 8 problems. Wonderful. Okay, done. We're done. Let me pause the recording here. Where's my recording? Here.